On with chapter 4. And last time we really talked about some experiments that led to our understanding of the atom. Out of that came really the sort of version of the atom that we deal with, which is we have a nucleus which has our protons in it, which are positively charged subatomic particles. Also, we have our neutrons in there, which have no charge. We found that basically the atom is mostly empty space, which is usually what's referred to sometimes as the electron cloud. And in that empty space, we do have electrons really, again, moving around, as we'll talk about coming up in the next chapter, in a really random sort of pattern. Again, they don't go in these nice, pretty circles or anything like that. We also talked about the idea that obviously most of the mass of the atom is made up of the nucleus. And that is because both protons and neutrons, each of them are about 1,800 or so times heavier than any electron that's flying around. With out of those three particles, as we talked about, the neutrons just edging out the proton in terms of the one that is the most massive. And we do see our electrons having an attraction to the nucleus as it is overall positively charged because it does have the protons in there. And that, again, is why we'll talk about in chapter 12, I think, why certain electrons, again, are involved in bonding and other ones aren't due to that sort of attraction to the nucleus. We talked about some other properties of atoms where we kind of finished up last time. We talked about atomic number. And remember that the atomic number is the number of protons there are within an atom. And the atomic number can be found on the periodic table. Once again, it is the number that is up on top of the symbol. That is the atomic number. As we talked about last time, that is the definition of an atomic number, which is the number of protons only. But again, if you are dealing with a neutral atom, because it has to be neutral and protons are positive, the only other particle there that has a charge are electrons that are negative. So if you're dealing with something that's neutral and you know the atomic number and the number of protons, then you should have an equal number of electrons in that case to balance it out to really a neutral atom. But once again, the definition there is just protons. We also talked about that if you look again on the periodic table, every element has its own unique atomic number, which means out of those three particles that we talked about, protons, electrons, and neutrons, it is the protons which are the most important in terms of what element you're dealing with, as no two elements have the same number of protons, so you'll know exactly, again, what element you're dealing with. Now, remember, all elements do have protons, electrons, and neutrons except hydrogen. Hydrogen has only a proton and an electron. It does not have a neutron, but everybody else will have all three of those sort of particles. The other sort of number we talked about there is the mass number. And the mass number is the number of protons plus the number of neutrons. So the mass number is both of those things together. Remember, as we talked about at the end there, mass numbers are not found on the periodic table. So very common, people make a mistake and think the number they see on the bottom is the mass number. It is not. So that, again, is the atomic mass, which we'll talk about obviously in a later chapter as well. But what confuses people sometimes, like I mentioned, is oftentimes the mass number and that sort of atomic mass that you see on the periodic table, they're very close to each other. So sometimes people just think they was rounded or something like that, and we don't do that. Again, the way that you can remember is when you calculate any of those things, protons, electrons, neutrons, mass number, atomic numbers, they all pretty much need to be positive whole numbers, so they all have to be whole numbers. And again, if you look at the periodic table on the bottom there, pretty much none of them are whole numbers, they're all decimal. So again, that's a good way to sort of keep that in mind. The nice thing about that is if you know the mass number and you subtract it from the atomic number, that will give you your number of neutrons. So that is how you can figure out how many neutrons something has, is take the mass number minus the atomic number, and that will get you your neutrons in that particular case. Any questions on any of that stuff there we talked about last time? Okay, so then let's continue on. One of those sort of points of Dalton's atomic theory that we talked about last time that was found to be sort of incorrect was the idea of Dalton's atomic theory that all atoms of the same element are identical to each other. They have the same mass and so forth. And the existence of isotopes, which were later discovered, sort of disproves, again, that part of Dalton's atomic theory. And isotopes are, as I mentioned, really the same element, but they have different masses. So in order for them to be the same element as we've been talking about, they do have to have the same number of protons because, again, that's what determines what element you're dealing with. So what gives isotopes pretty much a different mass is actually they have a different number of neutrons. So the isotopes are basically the same element, but they will have different numbers of neutrons. So they'll have the same atomic number, but the mass number typically will be different because of the different numbers of neutrons. Those also different numbers of neutrons do give isotopes some different properties. A lot of isotopes of elements are radioactive because of the sort of number of neutrons that they have versus protons. And it will definitely give you some different sort of, like I said, properties. Now, some examples of that is hydrogen, 1 proton and no neutrons, as I mentioned a second ago. An isotope of hydrogen is known as deuterium. It's sometimes referred to as like heavy hydrogen, and it has 1 proton and 1 neutron. And something like tritium, which is like the radioactive version there of hydrogen, has 1 proton and 2 neutrons. These are all called isotopes. And the way that we commonly write sort of the symbols for isotopes is, as you can see there on the bottom, we use the symbol, and on the top left of the symbol, we put the mass number. On the bottom left of the symbol, we put the atomic number there. So that's a very common way that isotope symbols are written. So as an example of that, if we deal with hydrogen here, we know it has 1 proton. That would be the atomic number, which means we would just go to the periodic table if you weren't sure what its symbol would be, and you would just find number 1 there, and it'll obviously tell you that hydrogen symbol there is H. Its atomic number, which is 1, goes there on the bottom, and we'll do that. Now we need the mass number, so remember the mass number are pretty much protons plus neutrons, which in this case is also 1. And this would be the symbol here for hydrogen, where we have our mass number up on top and our atomic number on the bottom. Now, again, if you have a symbol written like this, pretty much to figure out the neutrons, you take the top number minus the bottom number. So 1 minus 1 gives you 0 neutrons that we see there in hydrogen. Now, this is helpful to know these type of things because, again, we get to something like deuterium, and you're like, I don't know what that is, right? I'm looking for like a symbol with a D, perhaps. But you're actually not, because what we do know, again, is it does have 1 proton, which means even though it has kind of a different name, it is still the atomic number of 1, which means the symbol for that guy would also be a hydrogen symbol there, or an H. The atomic number here is going to be 1 on the bottom, which is our number of protons. And here for our neutrons, it has 1 proton plus 1 neutron. That is a mass number there of 2, and that's what would go up there on top. Once again, if you take the top number minus the bottom number, 2 minus 1 gives you your 1 neutron that deuterium has. So again, even though it doesn't sound like hydrogen, it is still hydrogen ultimately because it has 1 proton. And again, that is what determines what element you're dealing with. If we look at tritium, which once again doesn't even sound like hydrogen, but if you know, again, it has that 1 proton, that's going to take us back to the same element there on the periodic table with an atomic number of 1, which means we would use the same symbol. The atomic number would go on the bottom. Here we would add our protons plus our neutrons, so 1 plus 2 is 3, and that would be our symbol there for hydrogen, which is our tritium there, which really is hydrogen. And again, if you take the top number, 3 minus 1 gives you your 2 neutrons. So essentially, if you have these symbols written like this, top minus bottom number there on the left gives you the number of neutrons. Bottom number is always the atomic number, and top number there is the mass number. Once again here, even though they're all sort of have different names, ultimately they're all the same element. And they do have different masses, each of these, because obviously the first guy there has no neutrons, the second guy has one, and the last guy has two. And each of those neutrons obviously is going to carry a pretty significant mass, as we talked about, and they would have different masses. Any questions on that there? Now, if we looked at something, say like this, copper 64, this is also a very common way that isotopes are written, kind of the symbol and the number, a dash, a number. So we want to kind of think about maybe what that number represents. And what we do know is, if you're not sure if that's the atomic number or the mass number, you could go to the periodic table and find copper. And we see that copper has the lucky number 29 up on top, which means 29 is its atomic number. So that means that this number here is not the atomic number, because that clearly is not 29. This is the mass number. So very common. Sometimes with isotopes, they'll do the symbol dash a number, and that number that you see there at the back end there is the mass number, again, not the atomic number. That would mean, by the way, here, if we wrote it the other way, we would have 29 on the bottom and 64 up on top. That would mean in this particular case here, copper, which is sort of not like it. Says it again. Copper there, number of protons would be 29. Obviously here, since it is neutral, as we talked about, there's nothing written there, which would imply that it has a charge. So if you don't see anything kind of in the upper right corner there of the symbol, you could assume that it is neutral in most cases. That would mean it would also need to have, obviously here, 29 electrons to balance that out. 29 positive protons plus 29 negative electrons gives you an overall charge of 0. To calculate my number of neutrons in this case, again, we're going to take our mass number, which is 64, minus our atomic number, which is 29. And that would tell us, in this particular case there, 35 number of neutrons. Yeah. Any questions on that one there? All right, then why don't we try some here, perhaps, maybe? All right, so for each of these, take a moment or so, figure out how many protons, electrons, and neutrons each of these should have. Okay, so let's take a look. So again, when we have the symbols written like this, once again, the top number being our mass number, which again is basically our protons plus our neutrons. Down here, we have our atomic number, which is basically our number of protons. In this case, we know right off the bat from the bottom number there that CO, which is cobalt, should have, in terms of protons, 27 positive guys. Here we also know it is neutral, so once again, upper right there, we would be looking for something written. Obviously, if there's nothing written, it is neutral. And that just means that we should, in this case, also have pretty much an equal number of negatively charged electrons. Once again, 27 positives and 27 negatives. Going to basically give you no charge, which is sort of what we see over here in terms of our overall charge. Our number of neutrons is going to be our mass number in this case, which is 60, minus our atomic number, which is 27, and that looks like 33 in this case. Yeah. Any questions on that one there? Looking at the next one, Cl is chlorine, and again, starting with the bottom number, which will give us our atomic number and our number of protons, we should, again, in this case, have 17. No charge written there, so we could assume that it's neutral. So in this case, again, it should balance it out with 17 negatively charged electrons. Once again, giving us kind of 0 for the overall charge. Our number of neutrons there are going to be 37 minus 17. Looks like maybe a 20 in that case. Lastly, here we have U, which is uranium. And once again, there is no charge. So might as well start with what's on the bottom there, which is our atomic number. We have 92, basically positive protons. With no charge means, again, a matching number of electrons, giving us, once again, the overall charge there of 0. Number of neutrons going to be a lot, 238 minus 92, buck 46 maybe, something like that, I think, yeah. Would be our number of neutrons in this particular case. Any questions on any of those there? Okay. So let's try a couple more here. In this case, why don't you write the symbols with both the mass number and the atomic number for each of these. In case you can't see the periodic table, we'll give you some help here. 36 there. We got nitrogen, 7, and iron. Okay, so let's take a look. So obviously here, krypton is Kr, so you'd want to go to the periodic table there. Once again, that would be our symbol, capital K, lowercase r. Here from the periodic table, we can get the atomic number from it, and that is the top number there. That is, again, the number of protons there are, and that would go bottom left. That's also important because that's going to tell us our number of protons is going to be 36. Here we do have our number of neutrons given to us, which in this case is 48. So remember, if we add these together, that will give us our mass number, and that's going to be an 84. So we're going to go top there, 84 in that case there. Any questions on that there? Next is nitrogen. Once again, go to periodic table to help us out, which is your friend here when you're doing this. So N for nitrogen. Once again, always can get the atomic number there from the periodic table, which is 7. Here again, they gave us our neutrons, so we could just add those together. So our protons being 7, our neutrons being 6, going to give us 13 for our mass number in this case by adding those together. And that will give us some type of symbol that looks like that, 13 on top, 7 on the bottom. Lastly here, iron, which is actually Fe. Has a mass number given to us, so we can again get the atomic number from the periodic table, which is 26. They actually gave us the mass number, which is 56, which should go up on top. That also allows us to figure out the protons, electrons, and neutrons. So in this case, proton-wise, we got 26 positive guys. Once again, it is neutral, so we could assume that it should have the exact same number of electrons. And once again, here to figure out our neutrons, we're going to take our mass number, 56 minus 26, going to get us a 30 in this case. Yeah. Any questions on any of those? Now, all these that we have done here obviously do not have charges. So while we're looking at it, why don't we talk about what happens when something does have a charge and what's sort of affected in terms of our protons, electrons, and neutrons. So why don't we just borrow a couple of these examples here. I think we'll just borrow the bottom ones and stuff. Here. All right. So let's say that we had obviously here, just gotta fill that guy in too, I think. Our number of neutrons, mass number, perfect. And our number of protons and our number of electrons in this guy would be 7 as well. Now, if we had something, say, like nitrogen, but it was actually carrying a -3 charge, and let's just say it had the same sort of numbers there. When we do come across something that has a charge, those things are what are referred to as ions. So ions are things with charges. There's actually two types of ions that we'll talk about a lot in this class, and that is a cation, and those are guys with positive charges, and there are anions, which are ones that have negative charges. So a cation is something that's positively charged, and an anion is something that is negatively charged. So when we look at this nitrogen that now has a charge, and as I mentioned before, that again is typically where you will see the charge written on the upper right of the symbol there. Let's think about sort of what is happening here in terms of protons, electrons, and neutrons. So clearly here on our neutral one, we got 7 protons and 7 electrons, gives us no charge overall. On our one with a charge, the number of protons is still 7. Why does the protons not change? If I change the protons, is it still nitrogen? It is not. So in order for something to gain a charge, it cannot be the protons that change. Otherwise, you don't have the same element anymore. You now change your element. So it can't be the protons. Clearly, neutrons have no charge, so they cannot affect the actual charge of it. So that does just leave electrons, which is actually the thing that affects the charge. We know that as well because we could calculate our neutrons just like we did before. That would be 13 minus 7, which would give us our 6 neutrons that we had in our original example. Now, in this case, the number of electrons does have to change here. Now, how many electrons would it have in this case? Well, we know overall the charge is -3, which means in this case it actually has 10 electrons, right? So if you take 10 electrons, which are negatively charged, and add 7 positives to it, I'll go like that, you get -3 there. Get rid of the negative on the back end there. You end up with a -3 for the overall charge, and that is because it now has more electrons than protons in this particular case, and that is where the charge comes from, which is the number of electrons. That is a negatively charged ion, which means that is an anion. And if we look at the difference in the number of electrons from the neutral guy, which is 7, to the one that does have a charge, did it lose or gain electrons from the neutral guy? Neutral has 7, the one with the charge has 10, so it gained electrons, yeah? And again, that is why it has an overall charge of negative, because it has, again, more electrons than it started with. By the way, that's what you know when you see something that has a negative charge, it means it gained electrons. How many electrons did it gain from its neutral guy? That is what the number represents. 3 minus 3 means it has gained 3 electrons, in this case from the neutral guy. Neutral guy, once again, had 7. This guy has 10, which is 3 more electrons. So the number of the charge that you see on ions is how many electrons were either gained or lost. And the negative means, in this case, that it actually was gained from the neutral. Any questions on that one there? All right, now if we look at something like iron, for example, and if we look at iron, we'll do with a +2 perhaps here. And we'll do the same numbers, so 56, 26. Once again, because it is iron and doesn't change, it's got to have, in terms of number of protons, still 26, which are 26 positive charges. Neutrons, it still has the same as it had previously. 56 minus 26 is 30. Once again, here our electrons change. So the number of electrons in this case would be 24 electrons in this case. 26 positive guys, 24 negative guys, leaves you a net of a +2 charge left over. And that is where the charge comes from, as you now have, in this particular case, more protons than you do electrons. So more positive guys than you do negative guys. That is a positively charged guy. That is a cation. And once again, if we compare the electrons in the neutral, which is 26, to the electrons with the guy with the charge, which is 24, it actually lost electrons. So cations are things that will lose electrons. Anions are guys that will gain electrons, as we'll talk about. Typically speaking, metals typically will lose electrons. Non-metals on the periodic table are those guys that typically will gain electrons for some reasons we'll talk about probably in the next chapter as well. Once again, the charge tells you what's happening. Positive means I lost from the neutral guy. 2 means I lost 2 electrons from the neutral guy. So again, the number and the either positive or negative gives you some information that's going on. So when things do make ions and they make something with charges, the only thing that's affected is the number of electrons. Once again, protons cannot change, otherwise the element changes, and obviously neutrons have no charge, so they cannot affect the overall charge of a sort of isotope, atom, whatever you want to call it there. Any questions on that one there? Why don't you try one? Let's do, let's say we had nickel. 60, 28, and a +4 charge. So how many protons, electrons, and neutrons does it have? And then let's also do, I can fix my bad 8 there. Go. Let's also do, let's do oxygen here. The -2 charge. And let's do 8 and 16. So for each of these, how many protons, electrons, and neutrons do they each have? Okay, so let's take a look. We'll start with Ni, which is nickel. Once again, from the symbol there, we can, our sort of atomic number can be found. So that's going to tell us our number of protons in this case is 28. Here, we could also get our neutrons by taking our mass number, which is 60, minus our atomic number, which is 28 in this case. And that's going to get us like a 32 number of neutrons. Here it does have a charge, which means we do not have equal number of electrons. We see that it is positive, so we should automatically know that it pretty much has lost electrons, as it is a cation from its neutral guy. And again, it's got 28 positive charges, which means in terms of electrons, it actually has to have about 24 there. Negative guys. That's going to give you a +4 left over, which once again is where our charge comes from. Again, in this case, we actually have more protons than we do electrons, giving this guy here a more positive charge because of the extra number of protons that are there. Any questions on that particular one there? Obviously here, if we had a neutral nickel, just for comparison's sake, and it was neutral, it would have 28 protons and a matching number of electrons. So again, in comparison there, we see positive means lost, and 4 is how many electrons, again, it lost from the neutral atom in that case. Look at the bottom one, which is oxygen there with a -2 charge. Once again, here our atomic number that we could get from the periodic table, but it's actually written here, so we know our number of protons going to be 8. In this case, it has a -2 charge, which means it's an anion. Also, once you see the negative, it should imply that it has gained electrons. And the 2 is basically how many electrons it has gained. That means my number of electrons in this case is going to be 10. 10 negatives and 8 positives leaves you that -2 leftover charge, which is what we have here on our oxygen. Again, because of the presence of the extra couple of electrons, our number of neutrons is going to be our mass number, top number, minus our atomic number, going to give us 8. Again, in comparison, neutral oxygen would have 8 protons and a matching number of electrons. So once again, here we do see our electrons go up by 2, which is what the -2 implies in this case. Yeah. Any questions on things with charges, how to adjust? So again, really just the electrons are the things you're going to adjust in this case. Any questions on that there? So clearly you need to be able to figure out the mass number, atomic number, protons, electrons, and neutrons, things with charges, things without charges. Any questions on any of that? All right. So as I mentioned before, one of the nice things about isotopes in a sense is for elements, pretty much all their chemical properties, a lot of times are determined by the protons and the electrons in an atom. The neutrons really don't play a role in normal conditions. And what that does is, for example, a lot of isotopes are radioactive versions of elements. So, for example, if you were doing some type of research and you were interested, say, in copper, like I did before, and you want to kind of follow where copper was going around in some type of mechanism, you could actually use a radioactive version of copper, like copper 64, and you could just follow the radioactivity as you're doing the experiment, and you'll know exactly sort of where the copper ends up because it will all be labeled kind of as a negative. Nice thing about sort of the radioactive version and the non-radioactive version of elements is, like in the body, pretty much does the same chemistry because they're basically the same element, other than they have different masses. So a lot of times in research, they use radioactive +U versions of isotopes. Also times in medicine, they use radioactive isotopes to do scans, also to treat, tumors and stuff like that. Sometimes they'll do those type of things. Now let's talk about the periodic table next. So the periodic table is obviously an arrangement of all the elements. And we got one up there on the wall. It has a lot of information on it, and we're going to talk about some of these different parts of the periodic table, some of which we've obviously just started talking about there with our atomic number. So when we look at a periodic table, the elements that are in a column on the periodic table are what are referred to as a group or family. Nobody uses family anymore, so most people use group unless you find somebody really old, I suppose. So we call them groups, and that is going up and down on the periodic table are groups. If you look at different periodic tables, you will see a bunch of numbering sometimes. You will see what is sometimes referred to as the A numbering. You'll sometimes see the B numbering. And then you'll just sometimes see just straight up numbering, like 1 through 18 type of thing. And pretty much this chemistry class and all your chemistry classes that you take for the most part, everybody usually uses what's referred to as the A numbering, and that's sometimes referred to as the representative numbering. So when you're doing the A numbering, it is numbered like so. It is, I'll do red, I think. Group number 1 is actually right here. By the way, we'll talk about it in just a second, but group 1 actually starts with lithium. Even though on pretty much every periodic table you have your friend hydrogen hanging out over there on top of it, but group 1 actually starts with lithium. Right next door is group number 2. We actually then skip everybody in the middle and we pick back up over here at group number 3, group number 4, group number 5, group number 6, group number 7, and group number 8. That is the representative numbering. They technically, each of those numbers is 1A, 2A, 3A, 4A, and so forth. I would say probably 99.9% of the people don't include A when they say it. They just go, hey, group 1, group 2, group 3. And that is where you could find those groups. So once again, when we say group 3, it is right here. It is not this group 3. Typically, I would say almost 100% of the time when somebody's talking about group 3. So make sure that you sort of follow the correct numbering. When we look on the periodic table, kind of left to right on the periodic table in a horizontal, those are what are referred to as a period on the periodic table. And there's 7 periods, so periods head this way on the periodic table. And there's period 1, period 2, period 3, period 4, period 5, period 6, and period 7. And again, they are heading across the periodic table. So there are 7 periods on the periodic table, and we deal with typically 8 groups on the periodic table going that way. Obviously, as we've just been talking about on the symbol there, are above the symbol on the periodic table, that is where we find our atomic number, which is our number of protons. When we look at the periodic table, it is actually broken up into 3 sort of categories of elements. There are metals, there are nonmetals, and there are metalloids, which are sometimes called semi-metals as well. Usually on pretty much all periodic tables that you look at, and even if they're not there, people like to draw this like little staircase kind of thing going on about here, right there around boron. So to the left, and not on this picture, but also the 2 rows there on the bottom as well, those guys are metals. And metals are good conductors of heat and electricity. They can be hammered into thin sheets. They could be pulled into wires. They typically will have a very shiny sort of appearance. Metals, for the most part, are solids at room temperature. The one exception is our friend mercury, which usually on a lot of periodic tables also is a different color. So you can see mercury up there is more of a blue sort of font. And mercury is actually a liquid under normal conditions rather than a solid. But most metals will definitely be a solid. To the right of that staircase and kind of upwards of the staircase, that is where we find our nonmetals. So our nonmetals are pretty much the opposite sort of description of metals. They are bad conductors of heat and electricity. They also are very dull. They're brittle. They're oftentimes used as insulators. Also very different than metals is for nonmetals. We have a lot of nonmetals that are gases, some are liquids, and some are solids. So you have a more varied type of state that you find for your nonmetals. This is also why when we come over here to our friend hydrogen, it is not part of group 1 because hydrogen is a metal or a nonmetal. It is actually a nonmetal, even though it's hanging out with all the metals that are below it. And that is why hydrogen is not part of group 1, even though on pretty much all periodic tables you'll find it there. The reason for that is hydrogen has a lot of unique properties, and in a lot of cases it kind of acts in certain times like those group 1 metals, which is why it's kind of over there. It kind of acts very similar to them in certain situations, but it's actually a non-metal. Years ago on periodic tables, they actually used to throw hydrogen on both sides, which was quite confusing to people. They stopped doing that for long years, but they used to actually put hydrogen on both sides because technically it is a non-metal. It should kind of be over there, but it has a lot of sort of properties and it behaves sometimes very much like group 1, which is over there. Also, when we talk about nonmetals, these are typically the elements that come as diatomic molecules. So remember, I think the other day, maybe we talked about some diatomic molecules. Some diatomic molecules, again, things like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodide. This is how each of these elements come when they are by themselves. They are uncombined. They come as twos. And a lot of those are gases. Some is a liquid and some sort of like a mixture of a liquid with some vapor happening. Once again, that means the way hydrogen normally comes is as 2 together. Oxygen normally comes bound to another oxygen, and that is again normally how it is found. So a lot of those sort of diatomic molecules, which are elements, are nonmetals pretty much, and that is where we typically will see them. When we look at the Next sort of classification, these are what are referred to as metalloids, or again, sometimes people refer to these guys as semi-metals. This is what is sometimes referred to as a staircase. Some books may include boron with it or not, but it kind of comes down like a little staircase action. As you can see, sort of its location is to the left of it, we have metals. To the right of it, we have nonmetals. So these metalloids have properties that actually fall on both sides. So these metalloids, some of them, the exact same element that it is a metalloid, will have some properties that would be classified more like metals. And that same element will have some properties that are very similar to what you see with nonmetals. So semiconductors and stuff like that. Yeah, so that's where you find a lot of those guys in that sort of region. And again, they kind of have properties that fall on either side kind of that staircase, the same element. In addition, when we look at our groups, some groups do have special names. So starting with group 1, which is over here, again, starting with lithium in group 1, hydrogen not a member of it. Those are what are referred to as the alkali metals. Right next door, beryllium, calcium, magnesium, all those guys, those are what are referred to as the alkaline earth metals. Group 1 and Group 2, which is the alkali metals, the alkaline earth metals, the word alkaline means basic, pretty much. And as we will talk about probably a little later on in the semester, that's where you find a lot of strong bases, or that's where a lot of strong bases actually come from. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide. So a lot of strong bases actually come from group 1 or 2 on the periodic table, and that's sort of where their names sort of come from as well. We come all the way down to group 7, which once again is over here. Group 7. That is our halogens. Those are a lot of those diatomic guys that we just talked about, fluorine, chlorine, bromine, iodide. They are found there in group 7 on the periodic table. Any questions on that there? Now, when we talk about the halogens, as I mentioned before, a lot of them are those diatomic guys, and they are very reactive nonmetals. I think maybe next week you'll do an experiment with those nonmetals. They also react with a lot of metals to form ionic compounds. And if they react with hydrogen, or they get hydrogen on them, you get things like HCl, which is like hydrochloric acid, HF, which is hydrofluoric acid, HBr, which is hydrobromic acid. So they make acids when they get H plus sort of attached to them in the aqueous or sort of water environment. As you can see there, fluorine's kind of a pale yellow gas. Chlorine's a pale green gas. Bromine sort of has a liquid. Iodide, I think they still do that part of the experiment, but you might do that experiment part of it. But iodide is kind of a purple sort of solid. So kind of turns things purple in their kind of natural sense when you see it. The another sort of group which is really important is right next door to the halogens. That is group 8 right here. Group 8 is the noble gases. That is your helium, your neon, your argon, your krypton, all the ons, your xenon, all those guys there. Those are noble gases, also sometimes years ago called rare gases by people. Noble gases pretty much means that they are chemically inert, which means they pretty much don't react with anybody. They'll react with themselves, but they really won't react with anybody else. Noble means sort of a set above everybody else. Now we have 2 rows on the bottom here. These are our lanthanides and actinides series. And if you actually follow the numbering, maybe I could blow it up a little bit there. You follow the atomic numbers on those guys. Here we go 56 and 57, and then we hit 72. This row right here technically goes right about there, is where they should be on the periodic table. And if you go right below it as well, 88, 89, 104, that row right there should technically go right in there. So those bottom two guys technically should go right there. That's why they're called the lanthanide and actinide series, because those are the elements on the periodic table that they actually follow on the periodic table, and that's really where they should be. They typically don't put them there because your periodic table would be huge. The only place I've ever seen it done is like 2 doors down in that classroom. They actually did it. It takes up the whole wall on this side because they spread everything out and stuff like that. In addition, there are transition metals, and transition metals are found between group 2 and group 3. So everything in this region are transition metals. They are still metals. One of the properties that we'll talk about when we get into naming for transition metals is they actually have the ability, a lot of them, to make more than one sort of charge. So they're able to, for example, iron can typically make either a +3 charge when it does, or a +2 charge when it does. Copper, for example, could do +1 or +2. So these guys typically in the transition metal region have the ability to make multiple sort of different charges that occur. And as we'll talk about with naming, that also means that you have to name them a little bit different because they're able to kind of do that. But they are still metals as you kind of go through there. Any questions on that? Yeah. They are. They're actually, it's a very good question. What I was just about to say, actually, which is sometimes people will refer to those two on the bottom as inner transition metals, because technically that's kind of where they should be in that transition metal region. So sometimes they are referred to the two on the bottom as inner transition metals. Yeah. Other questions? Now, as you go, obviously, from left to right, you are going from more metal sort of characteristics to more non-metal characteristics. They did a really good job as they were building the periodic table. They left sort of spots in it and kind of filled it in as they went along. And obviously, things that are in the same group or things that are in a similar period or same period, they do have very similar sort of properties a lot of times. Um, and reactivity, as we will talk about as well, does depend, for example, where you are on the periodic table. As we'll talk about in later chapters, that's why when certain cases, when like a metal and a non-metal get, it forms a very, and when two non-metals get together based on their location and sort of their properties that they have. And we'll talk about some of that as we get going in some of those other chapters. Any questions on the periodic table? So obviously you need to know the periodic table. You need to know which way groups go and the group numbering, the A numbering, the 1 through 8. You need to know which way periods go. You need to know where the alkali metals are, the alkaline earth metals, the halogens and the noble gases are located, where the transition metals are essentially located. Any questions on that there? You will at some point, as we're getting close in a couple of chapters or so, getting into naming of everything. You do need to have some recognition sooner rather than later, probably would be really helpful, of symbols and their names that go with them. So that's definitely going to help you as we get into this couple of chapters down the road with the naming and the rules you have to follow. So I would, if you haven't done so, start getting so pretty familiar with the symbols and the names that go with those elements. All right. As I mentioned before, noble means the class set apart. There's actually, in addition to the noble gases, which are group 8 on the periodic table, there are some elements which are referred to as noble metals, and that's your gold, your platinum, and your silver, which should be right about there. You're right there. They're kind of gold, platinum, and silver. Those are noble metals. They're also very unreactive. That's how, for example, pawn shops and other places sometimes used to test your gold. You'd bring in gold, they would throw some acid on it, and if it was still there, it's probably real gold, right? And if it's not, it was probably fake gold. So you can hit something like gold with a really strong acid, not much is going to happen to it. It's pretty much unreactive and stuff like that. So we have some noble gases, like our noble metals with our noble gases as well. Now, our noble gases, as I mentioned, actually are what are sometimes referred to as monoatomic gases. They actually come as one. So, unlike hydrogen gas, oxygen gas, and who did I miss there? Oxygen, nitrogen gas. Our noble gases actually come as monoatomic, which means they just come as one atom, how they normally come. As I mentioned before, they're very unreactive, and that is what is sometimes referred to as being chemically inert. They are found monoatomically there, and again, our noble metals, kind of the same idea. They are probably the least reactive metals, and they are found usually uncombined in nature. So as we kind of talked about, obviously we have those diatomic molecules, which are our elements. And again, here's a little table of some of those guys. And you should know these seven. That is how they come. So it's really important. That's where people make a lot of mistakes sometimes is they may be given like something in words, for example, and they have to write an equation and they say like hydrogen gas and they just write H. And then they just wonder why they can never balance the equation or anything like that. So you have to remember that if they are not combined with anything, these seven, this is how they naturally come. They come as twos. Everybody else on the periodic table pretty much will come as ones if they are by themselves, not combined with anybody else. Again, if you had a piece of iron metal by itself, it would just be Fe, like if you had to write the formula for an equation. I think we talked about it last time, but just a reminder that things on the periodic table, if they are by themselves and uncombined, they do not have charges. So they do not have charges, as we will talk about in a later chapter, maybe towards the end of this chapter as well. Things really only get charges when, for example, metals and nonmetals hook up. That's sort of where they kind of get their charges from, and they become things that have charges, positive and negative. Now, the structures of solid non-metallic elements can vary. So you can have a different form of an element, like a non-metal, and these are what are sometimes called allotropes. Allotropes are really the same element, but the way they are kind of put together is different. So, for example, if you take carbon, a diamond is all carbon. Graphite, like pencil lead, is carbon. And fullerenes, which are like 30 or more carbons put together in a kind of like a soccer ball sort of pattern, if you will, like what a soccer ball looks like. Graphite, they're more put together, the carbons in sort of layers, right? Kind of like your pencil lead. And a diamond obviously is put together in a different pattern. And depending on how that carbon is put together, it will cost you a lot more money depending on which one you're trying to buy, right? A diamond versus some pencil lead as we get near Valentine's Day, right? So that is what diamonds arrangement is. And again, you can see it's very different than sort of these layers of carbon when they come together, sort of in graphite. But ultimately, they're both really just carbon, and they are allotropes basically of each other. So let's talk a little bit more about ions here, and we talked a little bit about it obviously when we were doing our protons, electrons, and neutrons. Ions, as I mentioned before, is really anything that has a charge associated with it. And again, it can be either a positive charge or a negative charge, giving you either a cation or an anion. And when we look at our cations, as we talked about, that is when somebody loses electrons. So if we look at something like sodium, which is a metal, neutral sodium will have 11 protons and 11 electrons. But when sodium loses an electron, it will then become an ion. So neutral sodium here with no charge, 11 protons, 11 electrons. Again, I know that because if I go there to the periodic table, sodium's number 11 up there on the periodic table. That would be its atomic number, and that would tell me the number of protons. When it loses one electron, it then ends up being a positive one charge because it still has 11 protons. Otherwise, it would not be sodium. But in this case, it has only 10 electrons. So 11 positives, 10 negatives leaves you a +1 charge. And again, that is where the charge comes from in this particular case. One way you could represent that in sort of equation form of somebody losing an electron is what we see here. You could have sodium with no charge going to sodium with a charge, and we see the electron on the product side. And when you write an equation and somebody is losing an electron, the electron will end up on the product side of the equation, like it's being given off or sort of lost in that case. By the way, both sides of that equation is balanced in terms of the charge. On the left-hand side, the sodium has no charge, so over on the left there is no charge. On the right-hand side, we actually have a +1 charge and a -1 charge from the electron. That equals 0 overall, and that equation is balanced in terms of what's happening with the charge in this particular case. So a cation, as we've talked about, is something that has a positive charge. The way that occurs, as we saw and we see here, is it will lose electrons. Maybe it loses 1 electron, 2 electrons, 3 electrons, however many electrons it loses. Once again, the positive charge here tells us it lost an electron, and the number of electrons is actually the number. Much like most things in chemistry, the plus there is usually how we write +1. We usually don't put 1 in most things. So here, when you just see a plus charge, that means it's a +1 charge and it has lost 1 electron. Any other number, we do put the number in, but if it's just 1, we just put a plus to represent that. Same thing here with magnesium. We look at magnesium up there on the periodic table. That's number 12. That means magnesium has 12 protons when it is neutral, and also 12 electrons when it is neutral. And that again gives us no charge. When magnesium loses electrons, it actually becomes a +2 charge. And again, we'll still have the same number of protons, which is 12. Gives us our positive. And for our electrons here, it will have 10 electrons, which is negative. Again, leaving us that +2 charge left over here. And again, we could represent that also as an equation. Magnesium with no charge goes to magnesium with a +2 charge and 2 electrons. Again, electrons on the product side here, indicating that that magnesium is going to lose 2 electrons along the way. Any questions on that? Now, if you have metals, and we'll visit this in more detail when we get into naming, but if you have an ion that is a metal, and I would say for our purposes here at this point, if it is not a transition metal, so is somebody not in that transition metal sort of region, the way that we name the ion is we simply just use the whole name of the metal. So for example, if you wanted to name your sodium here with a +1 charge, this would be known as the sodium, and then you just slap an ion at the end of the name, and that would be the sodium ion. If you wanted to do this guy here, which is our magnesium with a +2 charge, you would use the whole name of the element. That would be magnesium, and you would just put ion at the end of it. And here, that's aluminum. We would call it the aluminum ion. So we do that really for all metals. We just use the whole name of it. As I mentioned a second ago, and we'll talk about later in that naming chapter, when you're dealing with transition metals, in addition to the name, you do have to put a couple extra things into that name. But ultimately, you still use the whole name of the metal. You just kind of have to add something for those transition metals that we'll talk about. But if it's not a transition metal, you just simply use the name. Any questions on that there? Now, an anion, as we've been talking about, again, is a negatively charged ion. It is a result, come here, there we go. It is a result of gaining electrons. And once again, if we take something like our chlorine, and again, if we look at our periodic table there, chlorine is number 17. So neutral chlorine would have, in terms of protons, 17 positive guys. In terms of electrons, it would also have a matching 17, giving us no charge overall. When chlorine gains a charge, it actually gains a negative charge, -1 charge. Once again, because it is still chlorine, number of proteins would be 17. But in this particular case, the number of electrons actually would be 18 electrons. Again, 18 negatives, 17 positives gives you a -1 left over, which again is where that charge comes from. Much like we see with our metals, we could also write an equation to represent what is going on here. And we can write, for example, Cl plus an electron goes to Cl minus. The electron here is on our reactant side, and that is typically where you would put the electron if you are dealing with something that is an anion and is gaining electrons. So it's like the chlorine is grabbing that electron and gaining it. Now, I will say in this particular example, we do know that chlorine by itself actually comes not as Cl, but it comes as Cl2. Yeah, it's one of those diatomic molecules, which means each Cl would actually gain 1 electron, which means if you wanted to kind of write a truly balanced equation, you would actually have 2 electrons and an arrow where it goes to 2 Cl minuses. Again, it's more of a balanced equation. That is truly what's sort of happening there. 1 electron from each chlorine, but since it comes as a 2-pack, each one gains 1. That gives you a total of 2 electrons overall that is actually being gained in this case. By the way, it is still balanced, right? 2 times -1 is overall -2 on the left. 2 times -1 is -2 on the right. So overall charge of what's happening with those electrons is balanced on this particular equation. So if you want to represent somebody gaining electrons, you would put the electrons on the right side. Same thing here with any other one. For example, the oxygen there, same thing. We would actually go O2 plus 2 electrons. Gives us 2O2. Actually, it would be 4 electrons. That's actually my bad. Actually, it would be 4 electrons in that case because each oxygen would gain 2 electrons. And that would give us a total of 4 electrons. And that's what we see on the right-hand side. Each one is a -2, and there's 2 of them, gives us 4 electrons. How do we name something that is negative and it's an ion? We actually do something different in terms of the name. We actually drop the last part of the name. And if it's an ion, we put IDE in its place. So this is chlorine. The Cl minus becomes the chloride ion. So IDE. Fluorine becomes the fluoride ion. Now, sometimes we actually take more than just a little bit of the end part of the name. O2 minus becomes the oxide ion. So if it is a negatively charged ion, we end the name with IDE. We kind of take out the last part of the name or a little bit more in some cases. If it is a positively charged ion, we just basically use the whole name of the element. Any questions on that there? What we typically have happening here is metals are typically the ones that will make cations, which are positively charged. Nonmetals are typically the ones that will make anions, which are negatively charged. And by the way, when you put together something that has a positive charge and a negative charge together and actually write the formula for it, it should always equal no charge. So for example, if I took a sodium ion and put it together with a chloride ion, right? When I put these together, +1 and -1 equals 0, right? So the formula when those two guys come together would be NaCl, no charge written in the formula, but it is actually made up of things that are actually ions. So when you put always a metal and nonmetal together that have charges, the formula that you end up with should never have a charge, but it actually is made up of two things with charges. So for example, if I took calcium and wanted to put together with chloride, if I put them together exactly like that, will I end up with something with a charge? I will, right? +2 and -1 leaves you a +1 left over. So to get this guy to equal 0 in the simplest way possible, do I need more calcium or more chlorides? I need more chlorides, right? -1 and -1 is -2 to balance out the +2. And the correct formula here would be CaCl2. Remember, the number goes to the guy to the left, right? And that would be the proper formula. No charge in the formula when they come together, but it is actually made up of these ions. It's made up of the calcium ion, and it's made up, obviously, of the chloride ions. Simple naming, obviously here we just put the names together in this case, so that is sodium chloride, right? This guy here, name of that guy is calcium, and this guy is chloride, yeah? So if you had a name, what you get when you put it together, for this kind of simple ones here, you just use two names that we talked about, the whole name of the metal, the IDE on the non-metal. We'll talk why we don't do anything with that too, and it's not dichloride when we get to naming, but trust me, it's not dichloride in this case, yeah? So it is just calcium chloride. Any questions on that there?